Hello and welcome to this video titled An Introduction to TCP. In this video I'm going to go over a brief history of how TCP came to be. We're going to do a comparison of TCP to UDP. I'm going to define this term of what does connection-oriented mean. And we're going to look at the various header fields that TCP applies when it creates a TCP segment. So let's start with the history of TCP. TCP was originally developed by Stanford University in the 1970s, and originally TCP and IP were part of the same program called the Internet Transmission Control Program. IP is a protocol suite and ARPANET was the network infrastructure. So as this mentions here, TCP in very short order was decoupled or pulled away from IP to keep them separate and to stay consistent with a layered approach to networking. All right, so what makes TCP different from UDP? Well, first of all, let's start and talk about what makes them the same. So both TCP and UDP create a header. That header goes after the IP header. Let's just draw this out right here. So if I had two IP packets, and these represent my IP headers right here, both of them would have a header after that. And that header could be TCP, or that header could be UDP. Now in IP, we know we have a protocol field that is a value of what is this IP carrying. If IP is carrying UDP, protocol value is 17. If it's carrying TCP, it's protocol value 6. Now what else makes TCP and UDP very similar to each other is that both of them are able to keep track of individual sessions of the exact same application by using port numbers. We have a destination port number, and TCP and UDP make use of that, and they have a source port number. This way we can multiplex or have multiple instances of the same application running on a host, and that host can keep track of those individual sessions by giving them different port numbers. Here is where the difference between TCP and UDP ends. TCP goes way above and beyond what we've just drawn right here. So UDP is connectionless. When a UDP datagram, or I should say when a UDP header is applied to your data, and then that data is given downstream to IP, there's no connection-oriented nature of that. In other words, neither UDP nor IP is concerned with validating that the destination exists, validating that the destination is ready to receive data, validating that the destination actually got the data that we sent. That's all connection-oriented. UDP does not do that. Also, how UDP expects to receive data from the upper layers is in small, discrete messages from upper layer protocols. If we have an upper layer protocol, an upper layer application that the way it was designed to work is send a constant stream of never-ending data downstream to layer 4 of the OSI model, the transport layer, UDP can't really handle that. TCP can handle that. And UDP provides no reliability or transmission. TCP, on the other hand, is connection-oriented. And it can work with any format of data, including a constant stream of bytes from upper layer protocols. And it gives us reliability with acknowledgements and retransmissions. Okay, so let's dig into a little bit more about what do we mean by a connection-oriented? What does that term mean? Well, a variety of things. Number one, TCP verifies the existence of your peer. It says, look, I'm not going to send data to that destination if I can't confirm the destination's actually alive first. UDP doesn't care about that. UDP says, oh, give me your data, I'll send it out. Is the destination there? Maybe, maybe not. I don't care. TCP does a validation check first. It negotiates parameters with that destination to control the exchange, the flow of data that's going back and forth. And TCP data is exchanged reliably using sequence numbers, acknowledgements, flow control, and retransmissions. And TCP can gracefully inform a peer of the need to close a connection. You see, if I sent you a string of UDP datagrams, bam, 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 you'd be sitting there wondering, okay, is there more to come? Should I sit here and wait for more? UDP doesn't say, I'm done, I'm finished, send you on your way. TCP does that. TCP says, finished, goodbye, I'm done with this. All right, so let's look at some of the TCP header fields with some emphasis on this reliability. So we know that just like UDP, TCP makes use of source and destination port numbers. So that is sort of common between the two. Now, the port numbers are different. In other words, applications that make use of UDP services will have unique port numbers that are different than applications that make use of TCP services. Most applications fall on one side or the other. Most applications, when the creator designed that application, that programmer had to decide, do I want this application to hook into TCP or do I want to hook into UDP? Usually it's one or the other. There are some applications out there that actually have hooks into both and can choose UDP or TCP to do what they want to do. But most are not like that. Now we also have a sequence number. So this is how we can confirm that you actually received my data. When I send out my TCP segment, there's going to be a sequence number in there that eventually you are going to have to acknowledge in the acknowledgement number field. We also have a header length about how long the TCP header is. Reserve doesn't really apply. Control flags. Now we're not going to talk specifically about control flags in this particular video. That's used more for when you initially set up a TCP session from the beginning, and that will be covered in a subsequent video. Window size. This is something that's really very fascinating with the way TCP works. Now imagine this for a moment. Imagine that you are the YouTube server, okay? You are YouTube and I am a laptop, all right? I send a message to you saying, hey, can you start playing for me the latest Avengers Endgame movie? No problem. So you start streaming it to me. Now, right now, YouTube is the only application I have up. That's the only thing that I'm doing on the network. So I'm just sitting back. Now my laptop is receiving the TCP video that you're sending down to me, okay? Now, let's say all of a sudden I start opening up other network applications, maybe another instance of YouTube and another instance of YouTube, and start checking my email, stuff like that. Well, all this stuff that's coming into my laptop, coming down to me from the network, it all has to be stored in memory someplace on my laptop while my processor processes those packets. I've only got a certain amount of memory. So when we first started and you were the only thing talking to me, all that memory was yours. You could send me that YouTube video as fast as you wanted and I could process it. But as I start opening up more and more instances of YouTube and now email and web browsing and other stuff, now I start having a problem. I start saying, oh, okay, I need you to slow down because I'm starting to get overwhelmed here. That's what the window size is for. You see, when you send me your TCP segment, I'm going to acknowledge it. I'm going to say, yep, I got that. Now, TCP is a little bit more complex than that. It's not, you send me one segment, I acknowledge it. You send me another segment, I acknowledge it. TCP doesn't work that way. Typically, the way TCP works is that you can send me a bunch of segments, and this will be negotiated. I will negotiate with you, hey, you can send me 10 segments, and then I'll acknowledge all 10 of them, or something along that nature. But here's the point, is that initially, when we do our negotiation of our session, I will tell you right at the beginning, hey, can you send me this YouTube video? By the way, you can send me up to like 15 TCP segments at a time because I'm totally free and clear, and then I'll acknowledge that big block. So send me big blocks of data at once, and then I'll acknowledge it every time you do that. But as I start freaking out, because I've got lots of things going on now, my memory's starting to get capped out, I can use this window size field, and I can say, hey, can you reduce that down to maybe 6 TCP segments? I know I previously told you 15, but can we shrink it down to like maybe 6 and then I'll acknowledge it? That's what the window size is used for. It's for me to be able to tell you, hey, you can send me more or you need to start sending me less. It's a way of me doing flow control, controlling the flow of information as you're sending it to me. We also have a checksum and an urgent pointer. And where the urgent pointer comes into play is, let's say that you were a Cisco router and I'm someone who's telnetting into you. Okay, I'm telnetting, I'm trying to get your command line so I can control you. All right, so I'm typing characters on my keyboard, okay, and all of a sudden there's a problem and I realize, oh, real quickly I have to hit the escape key. Something's happening on you as I'm typing my characters and I realize that you're about to crash and die, so I need to hit the escape key on my keyboard and send that to you, and I need you to process that escape key right now, because if you don't process it, something bad's going to happen. So this is where when I send you when I send you my TCP segment that's got the escape key in it, I might set the urgent pointer saying, hey, this is urgent. You need to process this right now. Maybe everything I've been sending you, you've been storing in your buffer, waiting till you got a certain amount stored up, and then you're going to send it up to your CPU for processing. The urgent pointer says, now, process this now, this is urgent. And then we might have some TCP options, and this is why we have a header length, because the header of TCP is variable in size. And then we have our data after that, which in this case would be your HTTP data or your FTP data or something along those lines. And that concludes this video on an introduction to TCP.